Neural networks are a foundational concept in artificial intelligence. They have uses in computer vision, robotics, and a number of tasks within natural language processing. So, um, in discussing neural networks, I'm going to use these two terms interchangeably: deep learning and neural networks. Really, deep learning just refers to the same thing as neural networks, just with some added layers and added complexity. So I sometimes I'll say deep learning and sometimes neural networks. What I would like to do with this lecture is to just give kind of an overview of what neural networks are, including terms like perceptrons and hidden layers and activation functions. And I'd like to highlight two types of neural networks that have been useful in particular areas of AI: convolutional neural networks and recurrent neural networks. And then, secondly, I would like to get a little bit deeper into a particular use of neural networks in my own research, which is word embeddings. So it's an application of neural networks for a particular kind of language processing. Okay, so first of all, um, as we look at applications of artificial neural networks, we say, well, what are they for? Well, the list is exactly the same as for machine learning, because really, artificial neural networks are just an advanced technique within supervised machine learning. So we're doing the same thing where we're starting with some kind of data, and in the case of supervised learning, we have some label, and we ask the machine to learn how to recognize patterns so that it can predict the labels of new data. So um, really, what artificial neural networks do is they just they're a way of getting more accuracy out of machine learning tasks. And so um, they are especially prominently used in areas where machine learning has had low accuracy. Not really an acceptable, commercially viable level of accuracy. But once you start doing the machine learning with neural networks, you start to have accuracy that actually, is meaningful. So, we see them especially in facial recognition and object recognition. So this has obvious uses in autonomous vehicles and in machine translation. So this diagram I have here up on the right shows how step by step to map from, I believe these are Chinese characters onto English characters. And finally, natural language processing has a number of tasks within it that also have benefited tremendously from neural networks. So really, when we think about neural networks, they're not something different from machine learning. They're just an advanced approach to it. So if you do a quick search on Google Scholar for this phrase deep learning, and you see that I've just filtered the results to stuff since this year. We've got 27,000 results, across a wide variety of domains. So you see, it's used in healthcare. A guide to deep learning in healthcare, interpretable deep learning for spatial analysis of severe hailstorms, and then something having to do with accelerated deep learning, radio modulation classification. So it's all over the place. It's a really hot research area right now because it does yield some pretty amazing results. Okay, so again, I just want to emphasize this relationship one more time, that in general, artificial intelligence is kind of a general term. We have grouped machine learning as a subfield within artificial intelligence, and neural networks are just something within machine learning. And finally, deep learning just refers to just more advanced neural networks. Okay, so let's think about what neural networks actually are, by tying it to something that we already know how to do. When we build a predictive model using regression, the main task that we're doing is coming up with these parameters, right? So we're trying to predict some dependent variable, and as a function of some independent, one or more independent variables. And what we want to do is say, okay, well, if we're trying to predict this y from these two x's, how can we come up with this beta 0, beta 1, and beta 2 such that when we combine them like this, it gives us a pretty accurate prediction for y. It won't always be right. There will be errors because the line won't be perfect. But the point is to select these betas such that we get the most accuracy we can. And so this is just the process of estimation. We're estimating these parameters. So in addition to just taking a weighted sum, sometimes we also apply a function to the weighted sum. So in the example of logistic regression, we're finding parameters for this weighted sum, but then we're also applying the logistic function to it so that we can take this, treat it as a log odds, and then apply the logistic function to map it onto a probability. Okay, so this idea of estimating a parameter or estimating a weight and then applying a function to the output of this weighted sum, this is really what goes on with neural networks. If we take this, this linear regression equation here and represent it slightly differently so that we have our x variables here on the left, and we are, each of these nodes here is an input that we are multiplying by a weight that's on this arc going from this node to this node. So this is going to be x1 b1 plus x2 b2 plus, and then this will just be 1 times beta 0. So this will be the weighted sum. So this is just a different way of diagramming this. And so on the other hand, if we take this bottom equation here, and we are once again taking the weighted sum, but then first we're, before arriving at the output, we're passing it through a function. Okay, so if we think about one of these, we notice a kind of a superficial similarity with these physical neurons that are in our brain, where they have these inputs and there's some kind of processing that goes on, and then they become outputs. And so for this reason, this act of taking a weighted sum and then producing some kind of output by means of passing the sum through a function, this is called a perceptron. Okay, if we link a bunch of these together, so instead of just having the single weighted sum producing your output, if you say, well, let's imagine weighted sums producing some output here that's then passed to another weighted sum that's passed to another weighted sum, and so we can link these together, then we're starting to talk about a neural network. Okay, so here's some more detail. So let me pull this data set up. Okay. So we've got this data set. I think we looked at it before, where we want to build a predictive model to predict whether certain customers. So we've got some historical data here. We've got 30 customers, and we've got, for each customer, we've got the number of times they called and then the number of years they were with the company. And then the churn code is a 1 if they have left the service and a 0 if they have not. So what we want to do is figure out some way to combine calls and years to be able to predict if somebody is likely to leave the company. Okay, so we're starting with some data. We're just doing supervised learning here, and we just want to get as accurate as possible. Okay, so if we look at how this is diagrammed here, we're going to take we're going to take a 1 and multiply it by 0, so that's going to be our intercept. And we're going to do this weighted sum where we're going to find a beta 1 and a beta 2 such that when we do this weighted sum, and then this is going to give us something that we'll pass through the logistic function to get an output, which is the probability that x or y, probability that y is equal to 1. Okay, so the probability that our dependent variable is equal to 1, so this will be the probability that the customer will leave the service. Okay, so we're just going to take the weighted sum and then pass it through this output. So this is what I'm doing in this spreadsheet here. I'll go ahead and just initialize this here. So the challenge here is to figure out, well, what should these betas be? So I want to get as accurate as possible. So what I've done here is in column E, I've actually just calculated the weighted sum, where I multiply the calls by beta 1 and the years by beta 2 and added beta 0 as an intercept. And so that's what is appearing here in column E. And then in column F, I'm applying the so-called logistic function that takes that log odds and turns it into a probability that somebody will leave the service. And this column here, don't worry about the details of this, but this is my way of assessing how accurate my predictions are. Okay, so this is the log likelihood function, and what I'm trying to do is to get the largest log likelihood I can. Okay, so the idea is we're trying to come up with these betas. So we just, start putting in some things, and we'll say, we'll try these, and we're now, we can keep just trying different weights until we get this maximum, or we can use the solver, which is something that does that for us. So we'll tell solver, okay, this is the sum of all these, and we're going to try to get the maximum of these. We want to maximize this by changing the values here. Okay, so that's something you can do with the Excel solver. And I'll just come here and I'll say, okay, my objective is this log likelihood. Okay, and I want to find the maximum. Okay, so get the maximum by changing the values in these cells. And I'll just take the rest of the settings, the default settings. Okay, and there it does. So it found beta 0, beta 1, and beta 2. Okay, so I have a predictive model now here where I can just take these, if you give me new calls and years, I can do this weighted sum, do the logistic function, and then calculate it. Okay, so that is, that's what parameter estimation is. It's just trying to find these weights. So we have our input, and we know the correct output, and we're just trying to find betas that will get us to that correct output. And so the idea behind neural networks is that we are, instead of just going directly, just doing one weighted sum and getting an output, we're saying, well, what if we do 3 different weighted sums and combine them in such a way that they wind up at after the weighted sums, each of these weighted sums is evaluated separately. Then we combine these 3 with some other function. So what we have here is the same setup here where we have an input and we have an output. But instead of only finding these 3 weights, now we have to find all these other weights. So there are going to be 3 going into this node. That is, this is weight 1, and this will be weight 2, but then we're also going to have an intercept. So there'll be 3 weights there, 3 weights there, 3 weights there, and then 3, or if we add an intercept, 4 there. So we're already up to 3, 6, 9, 12 or even 13 different weights that we have to find. Okay, and we can do that. We do it the same way, where now I've got the same data, and I've got my calls, my years, and my churn code, just like before. And now each of these, this H11 refers to hidden layer 1, node 1. Okay, so there's only one hidden layer. So this is a hidden layer because we're not really interested ultimately in what winds up here. We're only interested in whether we get something close to the predicted output. So we call these hidden, and we calculate. So we calculate, what goes here by doing a weighted sum of each of the calls and years. A weighted sum there, and then a weighted sum at node 2, a weighted sum at node 3. Um, and this time, so this time, these are all these weights that I have over here. So this is the hidden layer 1, what you multiply calls by in hidden layer 1, hidden layer 1, um, node 1 years. So this is what you multiply years by to get to the hidden layer 1, node 1. And this is the hidden layer 1, node 1 intercept. So these three go into that first node there. And so these three go into that second node, and these three go into that third node. And then actually, so I do have an intercept, so now I have all these 4. So I have to, so the concept is the same, but we just have to come up with a lot more weights. And it turns out that this is ultimately the power behind neural networks, because with all these weights, there's a lot more freedom, more degrees of freedom. And so when we estimate these parameters, we wind up getting, something that's more accurate usually. So I'm doing the same thing here. I have a slightly different function that this time I'm minimizing something called a cross entropy. But again, this is just an evaluation of how close my predictions are. So I'll do the same thing here where I just say, I tell Excel, okay, go ahead and this time minimize this, which is really a measure of how inaccurate my predictions are. Minimize it by changing the values in these. Okay. And so I'll accept everything else, and it does it. Okay, so it just kind of worked backward to, once we set up all these connections, these calculations, then we just said, okay, if you want to go from this input to this output, change all of these weights in such a way that when you combine them, you wind up with a pretty good prediction. Okay, so this is what estimation is, and with a neural network, you're just doing a lot more weights. Okay, now this is okay. I mean, this is not too difficult, not too uh, demanding in terms of computer resources. But then once you start getting into something like this, there's, we just had one hidden layer with 3 nodes, and then we only had 30 rows of data. In this case, we have 1, 2, 3, 4, 5, 6, 7, whereas here we only had 2 inputs. Here we have 7 inputs. We have 1, 2, 3 hidden layers with multiple nodes on each, and then we have actually 10 outputs. And so now look at all the weights you have to come up with. So it's a real challenge to, just imagine, hand trying, experimenting with all these different weights until you have the optimal, fit. And so this was a big stall until there were improvements in, we need a large amount of data. We needed the back propagation algorithm, which, you know, uh, lent some real efficiency to finding these weights, and we needed hardware. So it turns out graphic processing units are really good at doing linear algebra, and finding these weights are really linear algebra. So these graphic processing units do a tremendous job of finding these weights efficiently. Okay. So in the process of putting together a neural network, you have all these decisions to make. You say, well, how many hidden layers should I have? How many units per layer? And then what activation function? So in this case, when I was doing this, I was taking these weights and then I was applying so these are the weighted sums, and then the predictions, so were actually the hyperbolic tangent. So I was taking the hyperbolic tangent. But there are a number of different functions, but the idea is that you're taking the weighted sum and then applying some function to it to transform it into something so that it can, fit some things that are nonlinear. Okay, so you have to decide on that is called the activation function. So in addition to how many hidden layers, how many units per layer, we have to decide, well, what activation function? And then finally, should we make it fully connected, that is dense? So we have every single node going to every single other node in this setup. Well, might we have a more accuracy if we don't have every single node connected? And so this is, what we do when we do this convolutional neural network. So with a convolutional neural network, you don't have a densely connected neural network. You still have multiple layers, but in this, in the process of estimation, it estimates not only the weights, but it estimates which nodes should be connected. And what happens with this process is that because because these pieces are all, linked together and others aren't, this actually starts to recognize subunits within something. So if we have an input image, this works really nicely with a so-called convolutional neural network, because with a convolutional neural network, it's able to connect in such a way that it's identifying little subparts within the picture. So here's a more elaborate um, uh, diagram of this. I'm not going to go into all these details, but the idea is that you have this visual input, and because it splits it out into these little subunits that it then recombines, it is identifying little pieces. So this is the um, convolutional neural networks have been the real winners when it comes to computer vision. So, any task involving, having to go through some image and identify pieces in it, identify whether somebody's wearing a hard hat or differentiate pictures of cats versus horses. Convolutional neural networks are the real winners there. So in addition to convolutional neural networks, we have what are called recurrent neural networks. So these general neural networks really, you saw that we just are passing our weighted sums forward. So there's not really any memory involved here, right? It's just going like this, where we're doing these weighted sums here, and then we're doing an output here. Well, this turns out, is great for images, and it's great for, kind of cross-sectional snapshot things. But because there's no memory, you can't really use a neural network for sequences. And so data that is inherently sequential, such as language or music, uses recurrent neural networks, where instead of just passing output to the next layer, it will use its own output in subsequent calculations. So this actually does result in some memory. So this is a very useful thing when dealing with language data. Okay. So one powerful application of neural networks within natural language processing is in this thing called word embeddings. The idea behind word embeddings is that if we're looking for individual words, as just trying to find them in documents, um, the individual word itself can have multiple meanings, um, or we could have things like homonyms, homophones, homographs that look the same but have different definitions, or we could have synonymy, where you have two different words that kind of mean the same thing. So instead of just looking at the syntactical makeup of an individual word, it would be nice if we could somehow move to a representation of individual words that actually encapsulate some of the semantics of a word. And it turns out that there's a good way to apply neural networks to do this very thing. So what we would like to do then is to say, well, instead of just having a word with some letters, is there a way that we can construct a vector, let's say of length 10, some kind of 10 element vector that would include all of the various semantics of a particular word. Okay, so let's think about vector representation. So representing documents as vectors is something that's been done for a long time, because what we've done is take documents and then represent them as vectors of numbers that are really counts of the words in the vocabulary. So for example, if each column is a possible word, let's imagine we have a vocabulary of 10,000, we have 10,000 columns, and each document can be represented as the counts of this word in this document. Okay, so as long as we have these consistent column positions, then each document can just be a 10,000 element vector, where we have zeros where this number's not there, and we have counts when the word is there. Okay, so representing a document as a vector is pretty straightforward. But how do we represent words? So one thing we could do is just take the transpose of this matrix, and we have words now, and each word has a vector, and this vector refers to the documents that the word appears in. So this is how one element of a search engine. So the reason you can just type in a word really quickly is because an index is made that looks like this, where you can find the word and then immediately just go across this vector and identify all the documents that contain the word. Okay, so but co-occurrence within a document is really kind of too big of a window, because you could have long documents, and so it include lots of words that don't really have any kind of relationship to each other. So we would like to constrain this context a little bit more and just say, well, what if we were only interested in words that occurred within some kind of window, like let's say 10 words, within 10 words. So let's say the word damaged. I would like to have a vector that somehow tells me which other words tend to appear within 50 words or within 10 words of this word. Okay, so there's this idea that you will know a word by the company it keeps. Okay, so if included in this vector is a summary of other words that tend to appear in this context of this word, then we actually are embedding in that vector some kind of semantics of the word. So, what we would like to have happen when we come up with these vectors is that we have some kind of space here where words that are similar, words that have certain meanings in common, would have similar vectors. So for example, we've got in this space here, we've got dog and cat on the same y axis, right? So their y elements are the same. And so this could be because, well, they're both domestic animals, okay? As opposed to wolf and tiger, these are wild animals. So these two also have the same y value, right? This should be 1, 2. Okay. Yeah. So these two have the same y value but different x value. So then what's on the x-axis? Well, if we see here, the wolf and the dog have the same value in the x component of this ordered pair. So this could be something having to do with canineness. And if we move over to this part, these two words have in common this this X element that probably has some kind of semantic notion of felineness. Okay, so this is the structure that we want from these vectors. So we've managed to take 4 words and express each of them as a 2-element vector, such that semantic information about the word is contained within that vector. So therefore, we actually are able to just do like a dot product or some kind of similarity of these 2 vectors, and it will tell us words that are similar. Okay, so the question is, how do we arrive at these vectors? So it turns out that you can use a neural network for this. So let's just, before I get into this diagram, let me just take a look at a toy problem here. Okay, so let's say that our corpus, this is our entire corpus right here, this one sentence. Okay, the quick brown fox jumps over the lazy dog. And I would like to come up with vectors for each of the words in this vocabulary. So the first thing I do is I just make I just make an ordered list of all of the words in the vocabulary. So we have 8 words total, and I would like to reduce this this particular vector of 8 down to 3, so that every word consists of no, actually, let's do 2. I want to have a window. No, let's do 3. I want to have a 3-element vector that for each of these words. So let's start with fox then. So I'm going to decide to take a window of 2. So I need to find all the words that occur within 2 words of the word fox. And so I come up with these pairs here. So I have quick, brown, and jumps and over. So all of those words are within 2 within 2 words of fox. So theoretically, if I can come up with some way of coming up with a vector that will map fox onto these other words, then that will, that vector will describe the context that the word fox tends to appear in. So the first thing we need to do is just come up with what are called one-hot vectors. So these are the one-hot vectors where each of the elements of these vectors refers to just a corresponding position in the vocabulary vector. So we have, so for example, the one-hot vector for fox is this one, where the only element set to non-zero is this one here that points to this position. Okay, so the one hot vector for quick is here and for brown is here. Okay, so what we want to do is say, well, how do we come up with a vector that we can multiply by this and then predict each of these? And so if we treat this as a neural network input and each of these as training examples of output, and then create a hidden layer that consists of 2 elements, this 2-element hidden layer, the weights on these 2 elements in the hidden layer will actually be the mapping from fox to all the words in the context. Now, how do we interpret these numbers that actually wind up in here? Well, we can't. There's no real interpretation, but we do know that it does contain what you need to know in order to predict these context words from fox. So let's take a look at how that actually works. So we have as input then that one hot vector for the word fox. Okay, so it's a vocabulary of 8, so there would be 8 inputs. We've decided that we want a 2-element word embedding vector. So there would only be 2 nodes here in this hidden layer. And there are, so the output is each word is going to have its one hot vector here as output. So we asked the neural network, okay, come up with some weights and then compute activations here at the hidden layer, and then come up with weights here that will predict these other words. Well, it turns out we don't need these weights. We're not going to actually do that. We're not actually going to predict the other words. What we're interested in is what winds up here on the hidden layer. So I've got a picture here where I show that we've got this this weight matrix here, but we're not interested in the weight matrix. We're interested in what the values that wind up here. And so it turns out that this is our word embedding. We've managed to take a vocabulary of size 8 and then reduce each of those to a 2-element vector that expresses the relationships of all the words that are within the vicinity of the word fox. Okay, so now instead of just looking in a corpus or documents or doing some kind of text categorization or summarization task using individual words, we can now use these vectors. And so instead of just having the structural lexical elements of the word, we have the semantic elements of the word. And it turns out that this has given text categorization tasks and a bunch of other NLP tasks a real leap in accuracy. I've taken just a few of the the recent developments that they've applied word embeddings to. I won't read all of these, but you can see that they're being applied to election prediction, material science, medical abbreviation expansion, speech recognition. Okay, here's an interesting one. Improving automatic categorization of technical versus layman medical words using word embeddings. Okay, and so on and so forth. So there's lots of exciting developments in natural language processing that result from word embeddings, and word embeddings are really just a trick of using a neural network to come up with a semantic summary of what a word actually means in terms of its context.